Okay, so what we're going to cover today is ideal diatomic gases, which basically means that we have more stuff going on internally within the molecule, but it's still a completely isolated molecule, right? There's no interactions. And then after this today, we're not going to talk about multiatomic molecules anymore, because the same logic applies, right? It just gets more complex when you go from 2 atoms to 3 atoms to 4 and so on and so forth, right? So then we're going to move on to interacting particles, which is by far the more interesting and more challenging of the aspects. Okay, so diatomic ideal gas. So in essence, what we're going to try and show today is why do we have a higher heat capacity for a diatomic gas by basically looking at the different energy modes of the individual system. So when we talk about a diatomic gas, we have a large number of potential energy modes. So we have translational, and what's different with the diatomic is now we have rotation, vibration, we have electronic properties, and potentially nuclear. So if we were to write these out, we have some partition function that is associated with all of the different energy states of the translation. Same thing with rotation, vibration, electronic, and nuclear. Right, so remember, the partition function is the summation of all of the different energy states. So the more energy states, the higher the partition function is going to be. The more possible energy modes, then you have sort of a multiplicative combination of all of the different potential states. So we have the total partition function of a particular molecule is just the product sum of every single one of the individual energy modes. Right now, in this assumption, we're saying that every single mode is independent, which for an ideal diatomic gas is probably totally fine assumption, right? So in this case, we have all of the partition functions multiplied together. And just to visualize this, we have a diatomic molecule. We have translation in 3 dimensions. We have potentially rotation in 2 dimensions. This is kind of hard to show. Maybe it's coming out of the page. We have vibrational modes. And then within each of the atoms individually, you would have electronic and nuclear. To simplify our math for now, we're going to say that we only exist in the ground energy state. So there's only one state possible. So the partition function is equal to just 1. Only one option. So now what we're going to go through in class is we are going to look at the forms of the partition functions for each of the 3 different modes. We're not going to derive them. We're just going to talk about how we typically model them and show how it fits into the big picture. Yes?
So we couldn't remove, like, say we were doing something like neon transformer, like neon light.
Mm-hmm.
We could not ignore number 4 or 5, right?
No, in that case you would not be able to. And so in the homework, which will be assigned early this week, you will actually be looking at plotting the heat capacity of a diatomic gas, and you will not be ignoring the electronic one. For simplicity, we'll just keep it simple for today, but the vibrational mode and the electronic modes, they kind of have similar sort of energy ranges of activation. Electronic is a bit higher than vibrational. But if you've gotten to the point where you're considering the vibrational energy, you probably should be considering the electronic energy states as well. And I'll be completely honest, I'm not terribly familiar with the nuclear energy states. So let's kick it off with translational. So we're going to model it almost exactly the same as what we did for a monatomic gas, but it's going to be a little bit different because the mass is different. It's got two different individual masses. So we're going to write Q trans to the 3/2 power, times by V. And for shorthand, we're going to write this as V over, I believe this is capital lambda, I think. And this is the de Broglie wavelength. So it's basically all the complex terms, not complexes and complex numbers. And has units of length. So M1 and M2 are the masses of the individual atoms in the diatomic gas. They could be the same in the case of oxygen, or they could be different in the case of something like CO. Okay, so this would be the same. We'll start a new slide for the next one. Now let's go on to rotation. So in rotation, we are going to use the model of a rigid rotor. This is also from quantum mechanics. The energy of a rigid rotor so I is the moment of inertia. And the D's correspond to the distance between the atom and the center of mass, basically where the particle is rotating around. So the degeneracy in this model is 2J plus 1. So as we increase the energy of the rotations, there's a number of different ways that we can be rotating in each of our different axes. So if we were to write out the rotational partition function, we're going to start off by assuming that everything is just being added up, right? It's a summation over all of the different states J. In this case, we're counting from 0 all the way up to infinity. We're going to take the degeneracy of each of the states multiplied by the scaled energy. So in this case, it's E to the energy scaled by the Boltzmann constant. Now, as it turns out, for rotational energy, the distance between the energy levels is actually relatively small, just like how we did it with the translation. So we can replace the summation with an integral of exactly the same form. Now, this is not going to be the case for the vibrational energy or for the electronic energy. Okay, so we're going to skip over the math, but we're going to define a few terms. So this theta R is defined as the rotational temperature. As units of Kelvin. So in our solution, if the rotational temperature is, if the temperature is much, much greater than the rotational temperature, we can integrate this expression above relatively simply. In which case, we get our solution that the Q rotation, the rotational partition function, is just equal to T over the rotational temperature. But this is in the condition that you're much higher than the actual rotational temperature. So I'll just rewrite that up here. In this case, I'll make it a little bit more clear. In this case, the sigma So in this case, this would be like CO. And this one would be like O2. So you have fewer possible states if you have a diatomic gas that is the same. Wait, yes. Because if you have the same, oh my goodness, I'm trying to say this right. If you have a diatomic gas where atoms 1 and 2 are the same, you have fewer total energy states because there's a degree of symmetry associated with the molecule. But if you have a compound like carbon monoxide, where the two gas molecules are different, then you have more states, in which case you have a larger value for the partition function. So if we look at values of the rotational temperature, they are on order between 0 and 100 Kelvin, give or take. So for example, hydrogen has a rotational temperature of 87.5 Kelvin, and oxygen has a rotational temperature of 2.8 Kelvin. So for most of our purposes, we can say that they are much greater. Yes? So there's no real concrete physical meaning, more of just a mathematical approximation. So if we go back, kind of like the de Broglie wavelength of sorts, whereas we're just taking all of the terms here, and we're just lumping it into one value, because it's going to be a constant, right? Because 8 pi is not going to change, the moment of inertia is not going to change, and Planck's constant is not going to change. So we're just taking all of the constants, lumping it together. Turns out that it has units of temperature, and then we're just sort of using that as a litmus test to say, okay, do we have enough temperature to be activating these energy modes or not? And that's basically the gist of what we're using it for. So it's just a simplification of the math to give us an order of magnitude analysis.
So if the temperature is less than this value, there will not be conditional heat?
You'll have some, but it won't be a lot, and you won't be able to. You will not be able to get this simplified of a integral expression. So this assumption here, when we integrate this integral is more complex than this down here. But if we take the limit that the temperature is much, much greater, we can make some approximations, and then that integral comes out more simplified. But if not, you'd have to have more of a long form. So if you were doing measurements in cryosystems, where you're looking at like liquid oxygen, liquid hydrogen, you might have to consider the deviations from this approximation. But good question, thank you. Okay. So these values here, just as a tidbit, these are from microwave spectroscopy. So, which has more energy? Microwaves or visible light?
Visible light.
Visible light. Which has higher energy, visible or UV?
UV.
UV. So if I'm going into the lab and I'm measuring a spectroscopic technique, right? If I'm looking at UV vis spectroscopy, what am I predominantly investigating in a molecule?
Visible light.
Well, what's going on with that molecule? When a molecule absorbs in the UV, how does it absorb that energy? So let's go back to our energy modes, right? Molecules can only hold energy in certain ways. How is it taking energy in the UV spectrum?
I agree with that.
No, it's not vibration. There's another spectroscopic technique that's very commonly associated with vibrations. UV is electronic structure you're probing, right? It's a very high energy structure. If I'm using IR spectroscopy, what am I typically investigating? Vibrations. Right? Do you guys remember, like, if you had that CO bond, you get that huge peak, or the OH? Right? So back in organic chemistry, you don't talk about, in undergrad organic chemistry, you don't typically talk about UV vis, but you talk a lot about IR spectroscopy. Okay, so then, if we're using microwave spectroscopy to look at rotational energy states, what does that tell us about rotational energy states?
Way less energy.
Super low energy. Right? So now if we're thinking about that in terms of how does light interact with our materials, the highest energy states are going to be the are going to be the electronic energy states, because that's when the UV vis spectrum is looking at it. IR spectra is looking at vibrational. Right? So what we're looking at now is the higher stepping up in energy states. So if microwave spectroscopy is what we're using to look at rotational, IR is what we use to look at vibrational, then we know that the vibrational energy states are much, much higher energy. Right? So this gives us connections between how we probe molecular behavior and how we understand how the molecules actually behave and interact. But for translational states, it's so very, very, very easy to accelerate these molecules, but we don't really have a good spectroscopic technique necessarily. At least, let's see. Oh, you can use neutron scattering. Yeah, so you can use neutron spectroscopy to look at that, but that's not in the scope of the class. Okay, so now we have a partition function for translation. We have a partition function for rotation. And the last one we have to cover before we can put it all together and look at how a diatomic gas molecule behaves is vibrational. So what we're going to use to model the vibrational energy of a molecule is a model called the harmonic oscillator. Which in a sense is two objects connected by a spring. with a particular spring constant. So the energy of a vibrational energy mode is given by this expression where nu, the Greek letter nu, and K is some sort of a force or a spring constant for the vibrational modes in between these two particles. The degeneracy for a diatomic vibration is 1. There's only 2 molecules, and those 2 molecules can only vibrate in one particular frequency according to this harmonic oscillator model. So if we look at our partition function for the vibrational energy modes, remember, we're just summing up all of the possible energy states scaled by the Boltzmann factor. Now, this is the approach for the canonical partition function, which is what we're still operating in, right? We're using all of the expressions that we've previously derived for the canonical partition function. Now, for this scenario, we cannot assume that the energy levels are so close together that we can approximate this summation as an integral. But the reason why the harmonic oscillator model was chosen is because it has a definite infinite summation. Right? So in many senses, we're kind of choosing the model to make the math a little bit more simplified. But the whole point around this in terms of statistical mechanics is that now we're breaking down the complex problem of predicting all the properties of an individual gas molecule by simplifying it into individual steps, right? So do we think that the harmonic oscillator is an appropriate enough model to fit the properties of a real gas? Right, so we're simplifying the question. In a sense, yes, it's appropriate. If we define a vibrational temperature in this case it is H nu over Kb. The vibrational temperature is much, much greater than the rotational temperature, and it is on the order of 1,000 to 3,000 Kelvin. So it is much, much higher. So this doesn't mean that below the vibrational temperature we have no activation of the vibrational energy modes. Right? And we'll talk about the limiting cases in a moment. Right? But it just says that the order of magnitude, this is a much, much higher energy mode to activate in a molecule. So ultimately, for all of these different models, we have to make implicit assumptions in the approach that we take, right? Because molecules are so very complex. We can only really derive analytical solutions for very, very simple systems, like a single hydrogen atom, right? As soon as we have multiple electrons, we really can't have an analytical solution to Schrodinger's equation. So the key thing to keep in mind is that even for the simplest of systems, we still have to rely on approximations. So in general, the vibrational temperature is a fitting parameter. If you want to boil it down to its real definite purpose. We're taking a model that we think is fairly appropriate for how the gas behaves or how the molecule behaves, and then we're saying, okay, we can't predict absolutely everything from first principles. Let's give ourselves a good shot, and then we'll just tune the model to make it fit. Okay, so if we take the harmonic oscillator, it has a defined summation. Now we have the partition function for each of the three modes that we're currently looking at. Now we should also be probably including the electronic partition function, but that's saved for the homework assignment. Okay, so we're putting it all together. So the partition function for a single diatomic gas molecule, ideal, meaning non-interacting, so the positions are completely uncorrelated and there's no energy of interaction, is the translational times by the rotational, and then the vibrational partition functions individually. So any particular molecule can have any combination of vibrational, rotational, and translational energy states. In this case, sigma is equal to 1. And the degeneracy is a little bit different. So if we just quickly, by inspection, take a look at this, the pressure for the canonical partition function is defined by kBT dln q dv at constant n and t. And remember that q for non-interacting particles is given by this expression. So from what we've seen, the pressure of a diatomic gas molecule should be exactly the same as a monatomic gas molecule, because the volume term only appears in one of the partition functions. The rotational and the vibrational energy modes have no relationship to the volume of the container that the particle is within. So the pressure of an ideal diatomic gas is exactly the same as the pressure of an ideal monatomic or polyatomic gas. All of the complexity that is introduced by having more and more molecules only concerns itself with the internal configuration, vibration, and rotation of that particular particle. But how it interacts with its surroundings only relates to its translational energy states. So there should be no difference from an ideal gas on how it behaves pressure-wise. Now, when we look at it in terms of internal energy, however, the internal energy is not related to the volume dependence, but rather the temperature dependence of the partition function. Right, so another way that we can think about internal energy goes back to exactly how we defined temperature in the first place, right? 1 over T was defined as in terms of our classical approach, right? So one way you can think about temperature is the relationship between the number of states and the energy of those states. And that's a very similar connection to what we see in the stat mech world as well. So as we increase the temperature, we have to be increasing the number of accessible states in our system, which will also increase the internal energy. So from a macroscopic perspective, temperature doesn't have a whole lot of significance. It's very convenient for us to measure, but in reality, temperature is the connection between the number of states and the energy of those states. But we can see from this expression here that we have temperature dependence in every single one of our new partition functions. So we would expect that temperature will have a big influence on the internal energy, right? But then, of course, the pressure doesn't change at all. Okay, so what we would be doing in translating this to Q is basically drawing a big bracket around this, raising it to the n power, and timesing it by 1 over n factorial. And this is our partition function. So when we take the natural log of the partition function, which gives us our first step into calculating the partial derivatives, getting ahead. There we go. So now all we need to do to calculate the internal energy is just take the partial derivative with respect to temperature and multiply it by kBT squared. And that gives us our internal energy of an ideal diatomic gas. So what I'm going to write out is the internal energy, excuse me, scaled by n kBT, just to keep it simple. We will get 3 over 2. This is for the translational energy. Right, should be the same thing that we've seen before, 3/2 n kBT for the ideal monatomic gas. I'm just writing it as 2 over 2 as opposed to 1 because if you guys recall from undergraduate thermodynamics or a physical chemistry course, it's often said that you get 1/2 contribution to the C sub V for every degree of freedom. So for translation, you have 3 degrees of freedom. For rotation, you have 2 degrees of freedom. Right? You can rotate this way, and you can rotate that way, but rotating this way is nothing. Right? It's a symmetric rotation. And then lastly, for the vibrational energy, it is not a very simple expression. So what we're going to do now is we're going to spend a little time looking at the limiting cases of the vibrational energy states and how it changes as a function of temperature. So quickly write out one last expression here, C sub V scaled by n kd. It's a little bit more tedious of a expression. So if we look at a couple examples of the vibrational temperature for a couple of different compounds. I think I have chlorine too on the next page. Chlorine has the lowest. So what we want to look at now is the limiting cases of this expression up here. So at low temperature, in this case, you have a very small temperature relative to your vibrational temperature, in which case your exponent is raised to a very large number. This ultimately goes to 0. The energy levels are just too high that you have a very, very small probability of any of your molecules being in one of those excited energy states. Or more likely than not, everything is in the ground vibrational energy state as opposed to one of the excited energy states. In this situation, your internal energy of the diatomic gas molecule is 5/2 NKBT, whereas the heat capacity 5/2 NKB. Almost exactly the same as the monatomic gas, except you have a little bit higher of a heat capacity because you also have ways to store the energy in those rotations. So conversely, not going to rewrite that function again, but the same function from above. In the high temperature limit, it just goes to 1. So in that scenario, your internal energy is 7/2 NkB/T, and your heat capacity is 7/2 NkB. So this gives us the low temperature limit and the high temperature limit of the heat capacity for an ideal diatomic gas. And in all circumstances, the heat capacity is higher than that of a monatomic gas, because it can only store energy in translational energy modes. So the more energy that you give it, all that it does is it increases its temperature by increasing the velocity in all of its different directions. So if we were to plot this out, and to plot out C sub V over N kB, so the heat capacity scaled by N and the Boltzmann constant, we have two limiting scenarios here. One which is 7/2, and down here, which is 5/2, and about in the middle, all right, 6/2. So for chlorine, the vibrational temperature is 814 Kelvin. So if we say this is 0 Kelvin, 1,000. So at T equal to the vibrational temperature, that same function from before, is about equal to 0.58. So in that scenario, the heat capacity over NkB is equal to about 6/2. So at the vibrational temperature, about here of 814, we have the heat capacity about there. At 0, we have the heat capacity at 5/2. And at very high temperature, eventually, we reach 7/2, our limiting scenario. And so then we can just sort of draw some lines connecting them. So one feature that you will never, ever, ever see is heat capacity decreasing as you increase temperature. And when you think about things from a statistical perspective, that makes a ton of sense. Why would you ever have a scenario where as you increase the energy state of the particle, it would have fewer, or whether you increase the temperature of the particle, you have access to fewer energy modes, right? That's never the case, right? The molecule will always find a way to put that energy into some different mode, whether it's a rotational, vibrational, translational, electronic, it will find a way to store that energy. So if you ever see a function that looks like this, then you know that something is wrong. And indeed, in the case of the polynomial fits that are very common in the classical world, right, you will see that kind of feature often. The reason by it is because it's just a polynomial. The whole purpose why they have selected a polynomial fit, in this case we'll say C sub p is equal to a plus bt plus t squared. Right, the whole reason why that particular polynomial function was selected is only because it has a simple to integrate expression. I, for one, know that I would certainly not want to be integrating a function that looks like this on a regular basis for calculating delta H's. Right? Our job would be much, much trickier if we had to deal with this kind of a function for every single routine calculation. But theoretically, that is the shape that fits the real physical process better. Yes, question?
Well, also, something else is because within any set data period, having, with a polynomial, you can have, X amount of degrees, however reason you need to get a very accurate representation of the data.
True. In theory, though, we could also take the same approach where we started off with this functionality here and then just added on some sort of a additional correction function as well. That could also accomplish a similar option. But yes, you can just increase the amount of terms in it. But from my understanding, the main purpose for this is simply because it is just very, very easy to integrate. And that's such a routine calculation that we do in classical thermo that it makes sense just to fit it. And we can deal with a little bit of inaccuracies here or there to make our calculations much more simple. But the key thing to take away from this is that the more complex the molecule is, in the ideal gas scenario, right, which is typically where we have all of our heat capacity data correlated in, it just depends on the internal structure and organization of that particular molecule. How easily can it vibrate, how easily can it rotate, which controls whether or not your gas, in the case of, let's say, let's go back to our table here. If we look at, let's see, nitrogen, for example, right? Its rotational or vibrational temperature is over 3,000 Kelvin, which means that nitrogen heat capacity looks a whole lot different as a function of temperature than does chlorine gas, for example. But the key thing to take away, right, is that no matter what, as you increase the temperature, the heat capacity always has to increase. The internal energy always has to increase. Because as you increase the temperature, you are always increasing the number of possible energy states. Right? And this is something that's an absolute law. And it gives us the functionality of how these behave. So now what we haven't talked about at all is interactions. Right? So when we talk about a real fluid, whether it's a real gas or a real liquid, right, you'll have to include additional contributions due to the intermolecular structure. Right now, we are only talking about the ideal gas state, which is basically a single molecule isolated in an infinitely sized box. So really what we're looking at here is the internal rearrangements and structures. So we have a way to readily calculate how we would expect heat capacities to be in these scenarios. But when we start to introduce intermolecular structure, then things get to be a lot more complex. Because not only are you changing how your particle is vibrating or rotating, but there's also energetics associated with the electrostatic interactions between your particle and the neighboring particle. And pulling those two things away will alter the energy of the system, changes the internal energy, changes the heat capacity. So interacting systems are much, much more complex. But in terms of ideal gases, if we understand the concepts of how we went from an ideal monatomic to an ideal diatomic, we can keep doing that for 3, 4, 5, n system. Right? And if you go through your book, there's a chapter talking about polyatomic gases and how they keep track of all the different energy states and the notations and the nomenclature, how they make the approximations. But in general, it's the same exact idea. Do we assume that the vibrational modes are dependent, independent? How do we model that? Sum it all up, take the derivative, and we can calculate the heat capacities. But from a conceptual perspective, it's the same thing, much more complex. When we go to interacting particles, it's a totally new conceptual framework. So that's where I like to spend the rest of the semester, is talking about interacting systems. Interacting gases, interacting liquids, and real systems. How do we measure it, and things like that. So we'll talk a bit about scattering theory, which is sort of my passion, I suppose. Okay, any questions on these systems? All right, so we are down to the last 4 classes. So basically, don't forget to hand in your paper to Canvas by Wednesday. If you have any questions about it, send me a message. I can take a look at it. I won't read it, but I will just skim it very quickly and say if it fits or not. If you are going to select a paper that has a predominantly experimental component, then the way to make up for it, to make it fit into the project mold better, is you have to talk then about what is the assumptions in the experiments, what is the apparatus, why is it designed the way that it is, things like that. But the purpose is to sort of introduce yourself to the terminology that is commonly used in the literature for thermodynamics, which is a little bit weird sometimes. Okay. Thank you very much. Have a good week.